Welcome to our presentation on synthetic aperture radar, made by me, Fereshteh, Katherine, and Sophie. This presentation will go over SAR, back projection, command and control, and the closing.
Synthetic aperture radar is a way of generating an image using radio waves. Waves bounce off of the Earth's surface to detect physical properties. It uses a synthetic array instead of a real array to receive data from the scanned surface. The radar sends pulses for each slow time to the ground. There are different methods of data gathering. The two shown here are strip map and spotlight mode. Once the pulse data of each pixel of the scanned ground returns, we can integrate the align returns to calculate a so-called reflectivity of each pixel. This is how back projection forms an image. It takes the reflectivity of each pixel and puts it in a plot. Here you can see examples of SAR images versus optical images. SAR images can detect how reflective the scanned surface is and are also useful in being able to see through cloud cover and the weather. Back projection also allows us to create cleaner images by not just focusing in the center.
Here is our progress of a Mona Lisa data file. Since our first attempt, we have implemented several techniques to create an upright, cleaner, and high-resolution image. We used vectorization to run the code faster, which allowed imaging at higher resolutions. We also used interpolation to create an accurate and smooth image. You can also see that the original data created the image with the X and Y axes flipped, so we ran the data differently to remedy that. In the bottom right, you can see our images for two other files. Interpolation is a NumPy function that takes three inputs: X coordinates at which to evaluate the interpolated values, X coordinates of our data, and Y coordinates of our data. It allows us to create regression with the Y coordinates of the data and evaluate on this regression for points we did not previously have in our data. Many calculations require to repeatedly do the same operation with all items in one or several sequences, which is usually implemented with for or while loops. These loops are set to account for every piece of data in a sequence individually. These will make your code faster than accounting for each piece of data manually, but this will not make it the fastest it can be. For example, when our team first created back projection, it took close to 15 minutes to generate a low resolution image. To solve this problem, we started using vectorization, which is a method to iterate over a sequence all at once, saving quite a bit of time. This method helped us go from 4 or 5 for loops down to 3. We also used this method to take our distance equation out of the innermost loop so that all of the distances would be calculated at the same time and not individually for each slow time. After all of the trial and runs and tweaking of the code, it went from 15-minute low resolution image to between a 60-second and a 5-minute high resolution image. This slide shows you all of the different types of data we have to use to create and plot our image.
The command and control section of our code focuses on communication between the host and the emulator using UDP socket programming in Python. The emulator is a separate program that simulates the Pulsar 440 radar. The initial phase includes the host sending a message to the emulator requesting certain settings, and the emulator sending a message back to the host to confirm it. We wrote code so that each time the host receives another confirmation message, we check all fields to make sure that the values are what we expected. After both devices are set up, the emulator proceeds to send scan data messages to the host. The client socket in the host keeps track of how long it waits to receive a message and times out once the emulator stops sending data. Next is data preparation. We sort the packets and check for missing ones. This is a consequence of using UDP to send messages. Even though it is fast and relatively simple, packets might get lost or out of order. Then we convert the encoded bytes into integers, substituting any missing data points with zeros. The final step is to feed the scanned data that we manipulated into the back projection code to form an image.
One of the many lessons that we learned over the course of the program was the importance of collaboration. Having to implement and work on two separate concepts at the same time that would eventually link with each other made communication and splitting up the work vital. We also learned debugging strategies such as putting print statements throughout our code to help determine the problem.
The following here is a summary of all the contents that we explained today. We just want to thank our classmates,
our UAS SAR staff,
the Lincoln Laboratory,
and Bob Shin.